So now for the second part of yesterday's lecture, we'll talk about gas transport and pH. So blood pH, normal blood pH is between 7.35, 7.45. It is maintained primarily due to the action of the respiratory system and the renal system. So those two systems work together to maintain a normal blood pH. So we'll delve more in depth into that with the renal system. Most of what we're going to talk about here is gas transport. So transport of oxygen and carbon dioxide. So if we start over here at the alveolus, we have oxygen entering the blood plasma, right? Oxygen dissolves in blood plasma, but the vast majority of it diffuses into red blood cells, combines with hemoglobin. CO2, on the other hand, is going to be carried in red blood cells and in the plasma, and it's going to diffuse out and into the air to be exhaled. This is referred to as loading. We tend to focus mostly on oxygen here. And then over here, as these red blood cells that are carrying oxygen get to the tissue cells, they're going to unload their oxygen. So dissolved oxygen is going to diffuse into the cells. Oxygen is going to be released from hemoglobin. CO2 is going to be picked up, dissolve in plasma. Some of it will bind to hemoglobin, some of it will be converted to carbonic acid. And then this cycle just keeps going. So we're going to have to match airflow and blood flow, and we call that matching ventilation and perfusion. So matching ventilation with blood perfusion in order to maximize gas exchange. So we're going to control bronchiolar diameter in order to try to match the ventilation with the blood flow. So things that will increase flow: if you have a higher than normal alveolar CO2 level, that'll be the strongest stimulus for bronchodilation. A low alveolar PO2 is a weaker stimulus, but it could also result in bronchodilation. Constrictors reduce airflow. Obviously, it's just going to be the opposite: low CO2 or higher O2. And that simply just means if CO2 is low, then the blood flow is picking up. You're not getting a lot of blood flow in order to deliver CO2 into the alveolus, and you're not getting a lot of blood flow in order to deliver oxygen from the air into the blood, so it's accumulating inside the alveolus. And so this is going to be about matching airflow and blood flow to maximize your gas exchange. There are other control mechanisms for bronchiolar diameter. Obviously, parasympathetic, sympathetic nervous systems, the autonomic nervous system. Right? Sympathetic stimulation during a fight or flight response. Epinephrine released by the adrenal medulla, travels through the bloodstream, stimulates beta 2 receptors. Right? Remember, beta 2s don't bind norepinephrine very well. That'll give you bronchodilation. This can be manipulated pharmacologically. So people with asthma, difficulty breathing because of bronchoconstriction, you can give them a bronchodilating agent, beta 2 agonist like albuterol. In order to help them breathe easier. Parasympathetic nervous system, via stimulation of M3 receptors, will give you bronchoconstriction. Humoral release, obviously any beta agonist will cause bronchodilation. Things like histamine and acetylcholine will give you bronchoconstriction. And leukotrienes, which we talked about when we talked about the arachidonic acid pathway, right? Eicosanoids. Leukotrienes give you bronchoconstriction during severe allergic attacks. Things like anaphylaxis. Now, control of blood flow to the alveoli. So before we were talking about airflow, now we're going to be talking about the denominator here. Matching blood flow. So dilators, things that will increase blood flow. If you have an increased tissue or interstitial fluid oxygen level, that'll increase blood flow to that area in order to be able to pick up more oxygen. That means that area is well ventilated. A decreased CO2 or elevated pH are going to be weaker stimuli for that. So constriction, if you've got an alveolus that is not being ventilated very well, so it's not getting a lot of fresh air, there's going to be a decreased tissue O2 in that area. So you would constrict vessels going to that area because you're wasting blood flow. So you have a mismatch if you send too much blood flow because you're not going to be able to pick up so much oxygen. And of course, CO2 and pH are going to be weaker stimuli. So alveolar PO2 and alveolar PCO2, remember Dalton's law, right? We're talking about partial pressures of gases, is determined by the ratio between ventilation and blood flow, our VQ match, our VQ ratio. They're inversely related through alveolar ventilation. So if you increase the VQ, you're going to get a higher O2 and a lower CO2. Right, you're going to be expelling CO2 faster when you increase this VQ. So hyperventilation is thus a way to reduce CO2. When you decrease the VQ ratio, this is going to give you a lower alveolar O2 and a higher alveolar CO2. Right, CO2 is going to accumulate and oxygen, you're going to be getting less of it. So hypoventilation, going to have that CO2 accumulating and being higher in the alveolus. So what are the only two places in the entire circulatory system at which gas exchange can take place? So you're going to have here pulmonary and systemic capillaries. So capillaries going through the lungs allow for unloading of CO2 and loading of oxygen. Systemic capillaries unloading of oxygen to be picked up by tissue cells, and then loading of CO2, metabolic waste product. Now that respiratory membrane is very thin. We kind of talked about that a little bit. The alveolus is made up of simple squamous epithelial cells. The capillaries are made up of simple squamous epithelial cells. And there's a little bit of connective tissue in between that basement membrane. So it allows for rapid diffusion of gases, O2 from the alveolus into the blood, CO2 from the blood into the alveolus. It's going to be aided by the fact that there's a thin layer of liquid inside the alveolus, and of course plasma is already liquid. And so we talked about, with Henry's law and solubility, the transfer of a gas from one liquid to another is very rapid, right? Almost instantaneous. But the transfer then from a liquid environment to a gaseous environment, or from a gaseous environment to a liquid environment, is much slower. And so what ends up happening is, because of this transfer between alveolar fluid and the blood, you're going to be getting oxygen and CO2 diffusing across that respiratory membrane at the same rate. And the primary driver then of this is going to be the concentration gradient, or the gradient of either oxygen or CO2. As I said before, pressure is going to be proportional to concentration. So we're, instead of using a concentration like milligrams per deciliter or something like that in millimoles, we're using partial pressure because they're proportional. And we know that the partial pressure is equivalent to the concentration. So if the concentration is 21%, then that means 21% of the pressure is also going to be contributed by that gas, in this case oxygen. Now CO2 happens to be 20 times as soluble in water as O2. One of the reasons that beverages are carbonated and not oxygenated. It's just easier to get CO2 to enter a liquid state than it is O2. Now the reason for that is just a little chemistry tidbit, the dipole moment, right, which relates to solubility in water. So there's going to be, if you look at the electron cloud for CO2, right, CO2 is not very electronegative, so the electron cloud is going to look something like that, right, making it more soluble, whereas O2, the electron cloud is going to look more like this, because both oxygens are equally electronegative. One of the other considerations is that air is humidified as it travels from the air into your lungs. So that water is going to occupy a part of the gas. So there's going to be a partial pressure of water as well. And that's going to displace some of the oxygen and CO2. So if you look at the PO2 in atmospheric air, it's going to be around 160 millimeters of mercury, whereas the PO2 in the alveolus is going to be closer to 105. Right? Remember, the concentration and the is proportional to the pressure. So as you add water vapor to the mixture, it's going to decrease the partial pressure of the O2 and the CO2 in the mixture. We're dealing with a respiratory membrane, so we have to deal with Fick's law of diffusion, which basically says that the rate of diffusion, which is called J, is equivalent to the concentration gradient, right? The surface area, right? More surface area means a faster rate of diffusion. The diffusion coefficient, which is going to be different for different molecules, and that's going to be over the membrane thickness. So as the membrane thickness, or the diffusion distance, increases, the rate of diffusion decreases, and vice versa. The diffusion coefficient for each substance is going to be determined by its permeability over its molecular weight, which gives you a number of different, the squirt, a number of different variables down here for each molecule, right? Solubility, the R constant, temperature, etc. So as an example, potassium has a lower molecular weight and is 30 times more permeable to membranes than sodium is. We've already established that from talking about action potentials and maintaining a resting membrane potential with potassium leakage current. So the partial pressures, we look at inspired air. CO2 makes up a very low component. We said roughly 21% is oxygen. Right, most is nitrogen, right, about 78–79%. And then this is going to be variable based upon the humidity of the air. So of course it's going to be humid air is more viscous, so it makes breathing more difficult. So if you're a runner running in humid conditions, breathing is more difficult than in low humidity conditions. By the time it gets to the alveolus, you've got a PO2 of roughly 100. You've got a PCO2 of roughly 40. And this is because there is air that is trapped, remember, in these bronchi, dead space, that is not allowed, doesn't participate in gas exchange. It just keeps the conducting zone inflated. And so that dead air accumulates CO2. So by the time the air gets down, it has accumulated some CO2 that is from air that's already in the lungs. The air is humidified, so the water vapor pressure is going to be higher. So the P, partial pressure of water in the gaseous state. Of course, nitrogen is going to change a little bit because as you add water, it's going to decrease the partial pressure of all the other gases in the mixture. Expired gas, right, the O2, you took some O2 out of what you inhaled, so it's obviously going to be lower than inspired air. CO2 is going to be much higher than what it was over here, because that's what you're getting rid of. You're going to breathe out more water vapor, right? The air was humidified when it went in. It's going to stay humidified when it comes out, which is why you can see your breath when it gets really cold. You've got that heat showing you the cloudy water vapor coming out. And of course a decrease in nitrogen because of the increases in some of the other gases, particularly water vapor. There are metabolic and endocrine functions to the lung as well. We talked about surfactant to reduce the collapsing pressure by Laplace's law. substances that get released into the blood. Many of them can be bronchoconstrictive. There are enzymes in the lungs that can remove things from the blood via metabolism. And then, of course, the renin-angiotensin-aldosterone system activation, conversion of angiotensin 1 to angiotensin 2 by angiotensin converting enzyme, ACE. So let's talk about the concentration gradient, these physical principles. The partial pressure we know is proportional to concentration. So the total pressure of the gas mixture is the sum of all the concentrations and the sum of all of the partial pressures. So if we assume that these are the percentages, concentration-wise, then that's going to be equivalent to the partial pressure. So the partial pressure of water vapor, the partial pressure of oxygen, the partial pressure of CO2, and the partial pressure of nitrogen. When oxygen is in the alveolus, it diffuses into the blood. And so the driving force is going to be the partial pressure or the concentration difference between the alveolus and the blood. So here we have a PO2 of about 100, and here we have a PO2 of about 40. So oxygen is going to move down its concentration from high to low into the blood. Most of that oxygen is going to be picked up by hemoglobin, and we have what's called an O2 sat, or saturation. That basically says what percentage of hemoglobin exists as HbO2 binding oxygen. And that saturation percentage should almost always be greater than 95%. So that means that 95% of the hemoglobin in your arterial blood should be bound to oxygen, should be carrying oxygen. The other 5% might be damaged. It might be carrying CO2 or something else. It's easy to calculate. It's easy to measure, but it's also easy to calculate by taking how much there is bound to O2 over the total hemoglobin concentration. Now we can also look at the content as how many milliliters of oxygen are there per deciliter of blood. And that'll give you a more accurate and absolute quantity. Oxygen has a relatively low solubility in blood. So normal blood has a low content as far as dissolved in the plasma. Your normal oxygen consumption is about 250 milliliters per minute. So if we were to rely only on dissolved oxygen, only on what was in the plasma, it would require a blood flow rate of 83 liters per minute. Your heart would be pumping like a hummingbird. So that's not going to happen. So what we do is roughly 97% of the oxygen that exists inside of red blood cells, inside of erythrocytes bound to hemoglobin. And it's a reversible binding. It depends upon pH and temperature, as do all binding reactions with proteins. They're all reliant on pH and temperature, because pH and temperature are things that, from biochemistry, you should remember, alter the three-dimensional structure of proteins. And hemoglobin's a protein. So hemoglobin transports about 1.3 milliliters of oxygen per gram. So if you think that a normal blood hemoglobin level is about 15 grams, then that's 20 milliliters of oxygen per deciliter of blood. A lot more than what is carried dissolved in the plasma. Now, if you're anemic, right, if you have a low hemoglobin anemia, then that total oxygen concentration is going to go down, because you're going to have fewer available hemoglobin molecules to carry oxygen. So here we have this binding curve for hemoglobin with oxygen, dependent upon the concentration of oxygen in the plasma, the PO2, how much dissolved oxygen there is. And you can see at a normal arterial level, normal arterial PO2 is 100 milliliters of mercury. 97% is going to be saturated. So that's your hemoglobin saturation, which should always be above 95. Unless there's some disorder, some pathology in the lungs, something going on with the cardiovascular system. Here, we'll look at 60. And you see the change between 100 and 60 is a decrease of less than 10% saturation. But at this point, the curve begins to change its slope and become a little bit more of a precipitous drop. So those receptors that exist in the carotid arteries and the aortic arch, right, aren't going to respond until arterial PO2 drops below 60. Then they're going to start to increase their discharge rate. You'll get the chemoreceptive response. Normal venous PO2 is 40. And you can see at 40, you still have 75% of your hemoglobin molecules saturated or carrying oxygen. But you've lost, in total oxygen content, a lot of oxygen to the tissue cells. So this dissociation curve here is going to help. So this is basically a binding curve of hemoglobin with oxygen. So that's going to help with oxygen delivery and oxygen loading, so loading and unloading of oxygen from hemoglobin based upon the PO2 of the blood. Now that curve shifts because of temperature and pH changes. So if we go to our Henderson-Hasselbalch over here, you have a pH equals the pK of carbonic acid of 6.1, and then the log of the bicarbonate over the CO2. Right, so the log of bicarbonate over the weaker acid CO2. So this shift is going to help us to load and unload oxygen. Right? Metabolically active tissues are going to have a higher temperature. Right? They're also going to have a higher CO2, which is going to give you a lower pH. Right? Because of this relationship that we've talked about before. More CO2 is going to shift the equilibrium to make more hydrogen ion, which lowers the pH. So in exercising muscle, the temperature is going to be higher and the pH is going to be lower, and that's going to shift this binding curve to the right so that you can unload more oxygen. Because that metabolically active tissue needs more oxygen. Right? So if we look at, let's say, a PO2 of 80 here, you've got a difference in saturation between about 90 here and about 80 here. So you're delivering more oxygen. There's less oxygen bound to hemoglobin, more is being picked up by the tissues. Metabolically inactive tissues then are going to have a lower temperature, causing a shift to the left, and a higher pH. That's going to favor loading oxygen, or hemoglobin keeping oxygen bound to it. All right, because that tissue is not metabolically active, or is not highly metabolically active, it doesn't need as much oxygen. So the shifting in this binding curve determines whether you're going to be loading oxygen or unloading oxygen. So a right shift at the tissue level will be determined by increased CO2, decreased hemoglobin affinity for oxygen, in order to maintain the partial pressure gradient. Left shift at the lungs is going to cause you to lose CO2, and it's going to increase hemoglobin's affinity for oxygen. So you're going to start loading oxygen. So here's a question. You can calculate the total blood oxygen content if you know the hemoglobin, which averages around 15 grams per deciliter of blood, the saturation, which we said normally in arteries should be 95%. If this were venous, it would be an SvO2. And then the partial pressure of oxygen in arterial blood is 100. So if you know those values, you can calculate total blood oxygen content, which is going to be how much oxygen bound to hemoglobin and how much is dissolved in plasma. So we know that each gram of hemoglobin carries 1.3 milliliters of oxygen. We know that there are 15 grams of hemoglobin in the blood. That was given. We know the saturation is 0.95. Right, so 95% of this 15 grams is carrying oxygen. And we know in the plasma, the PO2, the amount that's dissolved, is 100. And then we know that there are 0.003 milliliters of oxygen per millimeter of hemoglobin. Right, so that's going to cancel the units and give us our answer in milliliters. So we're going to have 19.1 milliliters carried by hemoglobin plus 0.3 dissolved in plasma gives us a total of 19.4 in the blood, about 20. Carbon dioxide transport is a little more detailed. It's not quite as straightforward. CO2 is 20 times more soluble than oxygen, so of course you're going to expect more CO2 in the plasma than oxygen, percentage-wise. In venous blood, you'll have 2.7 milliliters per deciliter. In arterial blood, there's 2.4 milliliters per deciliter because you got rid of some of that CO2 in the lungs. You expired it. So then that amount that was transported is 0.3 milliliters per deciliter of blood, which comes out to about 7% of your total CO2. So about 7% of the CO2 in your blood is dissolved in plasma. Most is transported as bicarbonate, approximately 2/3. So the CO2 readily diffuses into red blood cells, gets converted to H2CO3 bicarbonic anhydrase. That freely dissociates as a weak acid into bicarbonate and hydrogen ions. Hydrogen ions can be buffered by intracellular proteins, particularly hemoglobin, so that hydrogen ion can be taken up and reduce the hemoglobin. And the bicarbonate can be transported out into the plasma in exchange for chloride, and that's referred to as a chloride shift. So if we go way back and we talked about the different concentrations of chloride in different tissue cells, that relates to this. Right, so the chloride concentration of erythrocytes is going to be highly variable depending upon their production of bicarbonate. So if we look at transport of CO2, CO2 is made by cells. The PO2 is going to be higher than the PO2 in arterial blood, so you're going to get diffusion down the concentration gradient from high to low. Some CO2 ends up dissolved in the plasma. Some of it gets converted to bicarbonate, right? This is going to represent about 2/3. And then the remaining 23% is going to be carried bound to hemoglobin. So this is going to be HbCO2. So the venous blood is going to have a PCO2 now of 45, whereas in arterial blood it was 40, because you picked up CO2 from the tissues as a metabolic waste product. Then at the alveolus, the opposite happens. The CO2 that's in the plasma diffuses out, right? So from 45 to 40, right, from high to low, ends up in the alveolus to be exhaled. And then that can be replaced by this amount of CO2 bound to hemoglobin. Hemoglobin lets go of CO2. The O2 level is higher, right? So it's going to preferentially bind O2 by that binding curve we looked at. And then bicarbonate exchanged for chloride, right? So the chloride is going to leave the cells as bicarbonate comes in, so that's an exchange process. Secondary active transport. Bicarbonate can then be combined with hydrogen ion that was released by hemoglobin so that it could bind oxygen, and converted bicarbonic anhydrase to CO2. Well, there is something, a property of hemoglobin called the Haldane effect. Deoxygenated hemoglobin can carry more CO2, and that will then exist as what's called carbamino hemoglobin, HbCO2. So as your PCO2 goes up, right, this is going to release CO2, the hemoglobin will, and pick up oxygen. And as the PCO2 goes down, oxygen, hemoglobin that has released oxygen can now bind CO2. So if your hemoglobin level falls by half, so from 15 down to 7.5 milligrams per deciliter, what happens to the oxygen carrying capacity of the blood? Well, it's certainly not going to remain the same, and it's certainly not going to double. We know it's going to drop. The question is, how much is it going to drop by? Well, if we look at, so we've got 19.1 carried on hemoglobin and 0.3 dissolved. Right, you're going to end up carrying a lot less oxygen. Buffer systems in the body. So now we're going to be talking about pH. Right? If you remember, a buffer is something that can donate a hydrogen or bind a hydrogen, take it out of solution, depending upon the pH. Now, the most important buffer of the extracellular fluid is carbonic acid, right, via this relationship that we've been talking about. Inside of cells, the most important buffers are protein and phosphate. And both phosphate and ammonia are important tubular buffers in the renal system that we'll talk about when we talk about the kidneys. Proteins, particularly hemoglobin, in the blood or in the inside of cells, perform an important buffering function because they have this structure with an amine group and a carbox acid group. So if the pH rises, right, so if the environment becomes more alkaline, you can donate protons to that surrounding environment, the intracellular fluid, in order to maintain a pH, a normal pH. The pH falls if you have excess hydrogen ion, then that extra hydrogen can be taken up by the amine group to give you NH3+. And so proteins are very important intracellular buffers. Roughly 60 to 70% of the buffering capacity is located within cells because of the large component, the large protein component within cells. So if somebody has an acid-base disturbance, we classify that based primarily on the pH, right? So a metabolic acidosis, so a pH of less than 7.35. If it's caused by a metabolic problem, then there's going to be less bicarbonate. Either you're making more metabolic acid and that's taking more bicarbonate out of the blood to buffer the pH, or you're not making enough bicarbonate. Now the response, the compensation for that, is going to be to decrease the amount of acid in the body, and the acid that you're able to get rid of most quickly is CO2 by hyperventilating. The renal system will also increase production of bicarbonate, but renal production of bicarbonate takes longer than simply changing from normal to hyperventilation. Respiratory acidosis, so you'll have, in this case, the pH again will be less than 7.35. But the cause here is respiratory in nature, so you're going to expect a higher than normal PCO2. To compensate for that, you will produce more bicarbonate to buffer that CO2. Right, you'll convert more CO2 into bicarbonate. So you'll increase renal bicarbonate production as a compensation for respiratory acidosis. Metabolic alkalosis, so now you're talking about a pH that's greater than 7.45. It's metabolic, so again it deals with bicarbonate. Either you're making less metabolic acid or you're overproducing bicarbonate. So in order to fix that, you're going to hypoventilate and retain CO2 so that the blood PCO2 goes higher, so that you've got more acid for that bicarbonate. So a decrease in ventilation and an increase in renal bicarbonate excretion. So you'll reabsorb and make less bicarbonate. Respiratory alkalosis, well, if it's respiratory in nature, you've got a pH that's higher than 7.45, and that's caused by a drop in CO2. So you've got less acid in the blood. Compensation is to then decrease bicarbonate. Well, how do you decrease bicarbonate? Well, you increase renal excretion of it by making less and reabsorbing less. Which brings us to what's called the Davenport diagram. We're going to get into diagnosing acid-base disturbances when we talk about the renal system. And this is kind of a quick and dirty chart that some clinicians will carry around with them in their peripheral brain or on their cell phone or something. And so if you know what somebody's arterial blood pH is, and you know their bicarbonate, you can then figure out whether they are in a normal acid-base state. Metabolic alkalosis, acidosis is down here at lower pHs, respiratory alkalosis, etc.